Good morning. Until today, in this semester, we have dealt with, very generally spoken, the structural details of cable-stayed bridges in their final stage. We've gone back to the historic development, and then we went through the steel, concrete, and composite cable-stayed bridges. We dealt with the details of the stay cables. Now, for the rest of this semester, meaning the 2 lectures in December and the 2 in January, we will deal with the structural design, with the design calculations for cable-stayed bridges. Of course, we all today do the final design for a cable-stayed bridge with computers. There is no doubt about it, and rest assured I have my cable-stayed bridges all designed finally, of course, with the help of a computer. But I want to show you how you can calculate all important forces, moments and normal forces of a cable-stayed bridge by hand. I do that because that is the only way to give you a thorough understanding of the inner flow of forces in a cable-stayed bridge, so that you do not have to use the computer as a black box of which the output you have to accept without having a possibility to check, meaning you have to understand it. So these hand calculations are still today, with the extensive use of computers, which is necessary, and I'm not belittling it, but in order to enable you to understand the flow of forces. Secondly, you can do a quick preliminary design for getting basic sizes of members, which you will need for developing a structural design from the very beginning. You are also able, with these rather basic calculations, to compare the costs, meaning quantities, of various systems you may consider in the very early stage. They are rough, but on the same level, so they are comparable. I will give you methods for that. And finally, once you receive, say on the checking side, working for a checking engineer, a very involved computer calculation, you will be able, completely independent of what the computer gave you, to check the basic results. It will be, say, the sizes of members and stresses you are calculating will be in the range of, I don't know, plus minus 10, 15 or 20%. But to make a 100% or 200% mistake, for that you need a computer. By hand, you will normally not be off more than, say, 10 or 20%. That is the reason why we will, in the next lectures, go in detail how to do it. And first of all, today we start with the outline of approximate methods for which we use different systems. And next time we will then make numerical calculations to find out cable sizes, bending moments, and so on. So today, in the first lecture, we go to equivalent systems, which means we cut out a part which we can treat again by hand. And in the second part today, we will then go to the complete cable-stayed bridge and give you some understanding there how to apply these equivalent systems and how to get the internal run of forces. We will, in the first lecture, deal with how to determine the system geometry, span length, tower height. Then we will calculate the normal forces on an equivalent articulated system. We will then calculate life load moments for a beam on elastic foundations. And we will calculate or determine the permanent load moments on rigid foundations. You see here already 3 equivalent systems as an approximation, and I will show some basic moments for the towers, longitudinally and transversely, and for the stay cables. And for all these cases, we will touch on non-linear theory, which in German we used to call second-order theory. In English, it's sometimes also called P-delta. So those 3 are used in the same meaning. Nonlinear theory, second-order theory, or P-delta effects are equivalent. Going back to very basic, if we have a typical 3-span cable stayed bridge, if we load the center span, then the loads are transferred by the forestay cables to the tower head, and from there they are anchored by the backstay cable in the hold-down abutments. That is the basic flow of forces in a cable-stayed bridge. If we have the life load in the side span, we have an interesting phenomenon which you must always be well aware of. How is the flow of forces for a side span loading? Of course, again, in tension in the cables, the loads go up to the tower head. But from end, again, the tower head is supported by the backstay cable. The forces are transferred into the abutment. But very easy just by looking at it, the side span loads create compression in the backstay cable. Be aware, do not forget. That's unusual. This is the basic difference, for example, between a cable-stayed bridge and a suspension bridge. A suspension bridge carries loads, side span or main span, always in tension in the main cables. Cable-stayed bridges, the backstays of cable-stayed bridges, the governing cables, carry side span loads in compression. Important and perplexing. How can that be? How can a cable carry loads in compression? Well, under permanent loads, not these transient life loads, we stress the backstay cables to a certain extent. And now life load creating compression in here means the tension from permanent loads is reduced by this amount of compression. So it becomes clear we need a certain minimum amount of forces in the backstay cable in order, if we get the compression from the side span loads, the slack of the backstay cable doesn't become too big. The effective E modulus must not be too low. But we understand we carry compression in the backstay cable by a reduction in the tensile forces from permanent loads. Now, first of all, geometry. How do we determine the most effective span ratio side span to main span? This is governed again by the behavior of the backstay cables. There are certain considerations. if we show here the main span length, and if we show here the ratio of live load to dead load, and then we have what I explained to you to the backstay cables, two phenomena. On one hand, these live loads in the main span stress the backstay cable. The more force, the bigger the cable becomes. The bigger, well, the more costly, so we want to keep it to a minimum. On the other hand, if we have then in addition the side span, we get compression in there from live load. So we have a fatigue loading in the backstay cables. It fluctuates additional tension from live load in the main span and compression, negative tension, in the backstay. So we have a certain fatigue range in the backstays, which is the sum of the tension from main span load, plus, in this case, it's absolute, the compression from the side span load. And the most economic solution for, and this is very much governed, this ratio, maximum load and fatigue load, by the span range. If we have a very long main span, then we get very high forces here, and if we have a long side span, we get high fatigue range. And our aim is to find the span ratio which from maximum load gives us just such a cross-section that this cross-section is just able to take the fatigue loads. Normally we say 200 Newton per square millimeters. I have told you that. And now we have in here this line. And this line determines the ratio in which just this happens, that the cable sized for the maximum load is just able to take the fatigue range. And now it depends if we have a railway steel bridge. Then the live load may be, say, 60% of the dead load, of the weight of the steel beam. And if we have a concrete road bridge, then we may have only 25% live load of the weight of the beam. And so if we go then here, this is the ratio, live to dead. If we go for a regular roadway bridge in here, where we hit this vertical line, then we find in these curves, we find a ratio of side span to main span of 0.4. And that's something you should remember. That is very typical, that the side span has 40% of the main span. Now, if we go to a railway steel bridge up with this 0.6, well, then we have only 30% side span length of the main span. Again, it's governed by the fatigue range of the backstay cables. The next question is, how high shall a tower be? Again, as I keep repeating, we want to achieve the minimum cost. In real life, we're always in competition, and the bridge which costs the minimum will win and will be built. So what is, in this case, governing the tower height is the amount of cable steel required. And if we go in this curve and have here, kappa is called here the ratio of tower height to main span length, and here are parameters for the total amount of cable steel required, then we see if we have very low towers that flat cables, we need a lot of cable steel to carry. And then we come here in the range, the absolute minimum is somewhere here, 0.4, 0.5, which is understandable, because if you ask, if you have a given height, which inclination must a stay cable have to carry a vertical load to have the minimum amount of steel? You can vary that, and you find very easily it's 45 degrees. So a 45-degree cable requires for a given load the minimum amount, and that would of course lead us to something 0.5, that the tower height is 50% of the main span. But naturally we then also have an increased height of the tower, which also costs. So we must find the minimum from the cable steel required plus the tower costs. And that minimum for a cable stayed bridge is in the range here, something like 0.2 or 1/5. A typical height of the tower is about 1/5 or 20% of the main span. So those are two figures you should keep in your head. Side span to main span, very often roughly 40%. Tower height to main span, about 20% or 1/5. And if you analyze many existing cable stayed bridges, you will find these ratios. Now, how can we very easily calculate the normal forces in a cable stayed bridge by hand? Meaning mainly normal forces, of course, the cable forces, that's of our primary interest, but also the compression forces, tensile forces in the beam and the towers. Now, for that, we use very simple, aesthetically determined system, which we call an articulated system, articulated insofar as we place hinges in the beam at every cable anchorage point. So we have a hinged system. The beam moments are 0 with the hinges. Why can we do that and still be realistically close to the reality? We can do that because the bending stiffness, and of course we have a hinge here at the tower, the bending stiffness of the beam and the towers brings us about 5% maybe of the deflections of a beam under load. So with our approximation, we cancel that and just say we neglect the bending stiffness. And then we come to the principal formula to calculate the cables and so on of a cable stayed bridge. Very simple. The load we place somewhere divided by the sine of alpha of the cable inclination. Vertical load gives load divided by sine alpha as the cable force. That's all we need. And with that, we can calculate all the cable forces. Basically, of course, it runs down that we calculate the square of the unit cable for unit load 1. The cable forces here always trigonometric functions, 1 divided by sine, basically. And then to get the elongation, which we want there, we would divide that by the modulus of elasticity of the steel and the area. Of course, there is also a second term which determines the shortenings of the beam and the tower, but we neglect those as well, because the beam area and the tower area is so much bigger than the steel area, we can forget about it. So with this formula we calculate the forces, and with this formula we calculate the deflections which we will need later. Of course, we have then the cable forces. We have the normal forces for a load here in the center, If we have a load in the side span, as I took pain to explain to you, same formulas, however, we get tension up here and we get the compression down here. So that's all we need to calculate all cable forces and compression forces in beam and normal force in the tower. Simple, Nespa. You can't make it simpler. We'll have a calculation example next time, and you see it works very well. If we consider what are the governing load positions, well, of course, if we have the main span loaded, I've just cut the bridge here, then the normal forces, which are the horizontal components of the cable forces, they just add up, in this case run through, and are taken up by the backstay cable horizontal component. The horizontal component of a cable, of course, is cable force times cosine. We know that. And the same if we have it in the side span. The second important consideration is we not only have puzzling compression in the backstay, we have tension in the beam. It's just from load balancing. So we build up a tension here in the beam, and that is carried or balanced by the horizontal component of the compression force here. So be aware, we can get not only compression in the backstay from side span loading, but also tension in the beam. We can summarize the thing if we have a continuous load, be it permanent load, be it uniformly distributed live load, and we assume that the stay cables are very closely spaced. We can say, okay, the normal force runs in the shape of a parabola, and we have at the tower, we have then a very simple formula. The biggest normal force, mean N in compression, then is dead load plus live load divided by twice the tower height above beam times L square. So with this simple formula, we can calculate the biggest normal force in the beam from full load, which is one force we need for sizing. A little bit different if we have a harp configuration, where you remember not the cables run parallel, but go not back to the backstay. They still have to be anchored in the backstay because the beam here has no bending or very little bending stiffness, so the cables are not anchored to the beam, only here. Okay, there we need the bending stiffness of the tower. For an intermediate load, the force runs here, must run up the tower to be anchored by the backstay. So we have here a certain bending moment in harp bridges, which is one of the reasons why harp configurations require a little bit more material, because we need a bending stiff tower, whereas if all the stays run together here, we do not per se need the bending stiffness in the tower. If we have a harp directly anchored here, like the knee bridge, for example, in Düsseldorf, then it becomes very simple because the forces run here to the tower, but because now this is a fixed point, they go back here, no bending in the tower. This is why such a harp with side span piers is more economic than a harp only with a hold down pier where we need the bending stiffness. Okay, now just thinking my time here is wrong. Yes, my timesheet, I don't know what happened there. Something is wrong. Okay. if we want to calculate the beam moments, then we use as an equivalent system a beam on elastic foundation, ein elastisch gebetteter Balken. How do we go by it? Well, we can, in the first step, we replace the elastic supports the stay cables provide for the beam by springs with the same stiffness. And then we we smear out the individual springs to a continuous elastic support. And then we know the influence line for a beam on elastic support, you find it in every handbook, runs like this. We need to calculate the deflection here, then the characteristic length, and get the influence line. And if we calculate all that out for a cable stayed bridge, then we know for if we have a concentrated load, track load, then the beam moment is 1/4 concentrated load times the elastic length we have calculated here, that parameter. And if we want a uniform load, the moment of a uniform load on the cable stayed bridge beam, then it's just if we integrate out all these sines and cosines which are there, 0.161 times the UDL, uniform distributed load, times this L squared. That's all. With these two formulas, we can calculate all the beam moments of a cable stayed bridge. Again, simple, isn't it? Now, you may say, well, how does that, is that true? Well, I have here a comparison for the same cable stayed bridge. The influence line here, dotted lines, for a beam on elastic foundation, and the influence line calculated by computer, and you see there's no difference. It is correct. And just a little word we will come on later. It is okay for the top positive branch. We do not get a good approximation for the negative moments. There the influence line differ. So we get only the positive, but they are governing anyway. So that's important. And now, by applying this beam on elastic foundation principle, we come to another puzzling realization of a cable stayed bridge. And that is the stresses in the beam of a cable stayed bridge. If we use an idealized cross-section which has only top and bottom flange, then the stresses are independent of the beam depth. If we have a given top and bottom flange, concrete, steel, doesn't matter, with a weight, a given stay cables with a given life load, and we vary the depth of the beam, say from 1 meter, 2 meter, 3 meter, the stresses will be the same. It's a little puzzling, and the proof is here. One can do it in various ways. I've always done it with a beam on elastic foundation. So this, of course, then gets us to the conclusion. If that is the case, then, of course, I will minimize the beam depth because I have the least wind angle of attack, for example, and so on. Well, then let's make it to 0. Then stresses are very small. Yeah. The limiting condition, however, is the buckling. I cannot have less depth or less bending stiffness, so that I still have sufficient safety against buckling, or practically speaking, I limit my increase of stresses due to non-linear theory. We come to that. But we can get rather close, and I will show you examples. You've seen bridges which are very slender, and the base is this. The stresses do not increase within certain limits if we decrease the beam depth. I mentioned we have the problem of buckling. Now, how can we calculate the buckling of a beam of a cable-stayed bridge? By hand, that's what I'm talking. Well, we go at the basic beam on elastic foundation under compression. Then the buckling load is the square root of the stiffness times the elastic support. If we have a real cable-stayed bridge, we have a more or less constant bending stiffness of the beam. We have an increase in the elastic, say, soil support for a beam on elastic foundation, because here at the tower we have the nearly vertical cables. The stiffness of the support becomes bigger. We have an increase of normal force over the length of the bridge. And if we calculate for every place from here, E is given, the I is constant, the beta increases, then we get a safety against buckling between we first calculate the buckling load itself from this formula, and then compare that with the actual normal force. Then, of course, because all that varies, it's not constant. It runs something like that. And then you can show generally that the overall buckling safety compared with this additional system is very close to the tower. So if we take this, we had here 13, and the true computer calculated buckling stiffness 12.7, close enough. So if we use the support, normal force, and stiffness at the tower, with this formula, we can immediately by hand calculate the buckling stiffness of the beam. Now, buckling stiffness is a theoretical value. What we are really interested in is the increase in stresses due to nonlinear theory. And this we can use another approximation. Then we say moment due to second order theory is to first order theory divided by 1 minus actual normal force divided by the buckling force. It's clear if the normal force is 0, then this is 1, M2 is M1, good enough. If the normal force is the buckling force, then this becomes 0, goes to infinity. So the border conditions are okay. In between, well, roughly. But it's an approximation. And I have just done here a little bit for a cable-stayed bridge. I showed you concrete bridge, Pesco-Kennewick. And there we had, although it's a very stiff bridge, already a 9% increase. That was the calculation of buckling, or we had the beam on elastic foundation. Now, the third approximation system, equivalent system, although it sounds strange now, is the beam on rigid foundation. For permanent loads, we assume that the beam is rigidly supported at the cable anchor points. That's our third equivalent system. We have the articulated system in the hinges and the beam for the normal forces. We have for transient loads, which go on and off, life loads, the beam on elastic foundation as an equivalent. And for permanent loads, we can use cable forces and beam gradient so that the moments are actually those of a rigidly supported beam. Those are the three we need. And now, what are the moments under permanent loads? Well, for a concrete bridge, I will explain a little bit later, rather tricky theoretically. We use really the moments of a beam rigidly supported at the cable anchor points. Why? Because every moment we choose here freely, we come to that in the next lecture, will creep to this stage. I'm confident you've learned all that in concrete structures, creep of concrete. So we must find a system for permanent loads which doesn't creep away, and just believe me, it's the system which is rigidly supported at the cable anchor points. We come to that later. Now, for a steel bridge, there we do not have creep, and we are free to choose the moments, and so we normally introduce under permanent loads negative moments, because the positive moments from live load are bigger. So we have here the minimum of material by super elevating the beam, and here we have the minimum amount by rigidly supported. Sounds puzzling, we come to that in detail later. Another little interesting thing, if we post-tension, this post-tensioning is permanent load, beam on rigid supports. And because the cable distance is in the range of 10 meters, we normally do not use up and down tendons, but straight tendons. And if we post-tension a beam with straight tendons on rigid supports, then the moments from eccentricity, which we caused MV0 at my time, from eccentricity and the restraint moments we used to call MV prime, they just balance one another. It's clear the curvature wants to go down but can't because of the rigid supports. So what remains from straight tendons, wherever they are placed in the cross-section, up, down, doesn't matter, the resulting post-tensioning force is only normal force, because the two moments from eccentricity and from restraint exactly balance one another. All these things are, of course, in some detail in the script, so you're most welcome to read it there, but I can't go into all these details here. I just give you an impression and leave you astonished, I hope. Now here we have a typical, talking of post-tensioning, run of tendons, something over the full length for construction, and then in the center and at the ends where we have less from the cables. Now, as I told you, this is now just a typical example. A cable stayed bridge. We see here the primary post-tensioning moments from eccentricity, post-tensioning force times distance from the center of gravity, primary, and here the corresponding restraint moments. And as I told you, it's all computer calculated. Don't believe me, believe the computer. They balance one another, the two. So all what these two balance one another, all what is left from post-tensioning is a normal force. Now, shrinkage and creep is a little tricky. I'll go through it fast because otherwise it's 2 or 3 lectures, but I'm hopeful you have all learned that in concrete structures. If we have a 2-span girder, then, and if we calculate the moment there as a statically indeterminate system, then that's QL squared 8. If we at the end of construction have a different moment there, then the difference between this moment and the rigidly supported, here we go again, this distance is reduced by creep by the amount delta m times e to the power of minus phi. And if we have during the life of the bridge a pier settlement, a slow support, then not the full elastic moment occurs, but a moment reduced by 1 minus I to the power of minus phi divided by phi. Basic writing there. So we have sudden pier settlements immediately after construction, rather big amount of creep, slow pier settlement, little amount of creep, but it always creeps to the standard beam on rigid supports. Now, cable stayed bridge, things are getting a little bit more involved, I'm afraid. But we have the two principles. We have at the end of construction certain beam moments which may differ from those which would occur if we have rigid supports at the cable anchor points. This delta M plötzlich, delta M sudden. On the other hand, due to shrinkage and creep, the beam shortens. That means this point goes to here, which means the cable rotates, which means the beam goes down, which creates moments from slow pier settlements, which are also reduced. And if we then combine these two, we come to this formula. We've only published it once 40 years ago. It's a little tricky to understand. It took me a little time. But if you are interested, this is the heart of shrinkage and creep with cable stayed bridges. And these considerations are the proof why I say permanent loads for a concrete cable stayed bridge are calculated as if the beam, the concrete beam, would be rigidly supported. Because only these moments, if they occur in the beam at the end of construction, do not creep away. They are constant, nearly. The nearly is all in the script. Okay, very briefly, towers. In longitudinal direction, we have a cantilever fixed here. This is the backstay cables. Now the backstay cables, by elongating, deflect the tower, so we get this deflected tower with the normal force, and depending on the ratio of this vertical component to the beam, to the tower stiffness, we have a non-linear effect. In this way, if that force is low, or tower is very stiff, we just have this linear moments. And if the tower becomes more and more slender, then this moment here decreases, can even change its sign. If we go for a stiff concrete tower, Pesco Bridge, even there, although it's a stiff tower, we have a little reduction in the linear moments, 77, non-linear decrease here, but of course they increase here. There's no such thing like a free lunch. We have to pay for, if we have a decrease here, we have an increase here. And these moments finally may look like this change sign here, but that's only possible with very slender steel towers. But it has been used. Look it up in the script. In transverse direction, if we have an A tower, we have tension and compression. It's a truss, or if we used to say in English, strut and tie analogy. Strut is a compression member, tie is a tension member, so what we call Fachwerk analogy, truss analogy, in English it's called strut and tie model. However, if we go together here, then we don't have a truss anymore, but we have more or less high bending moments. That's why towers underneath the beam in this shape increase their size here, their depth. Here it can be constant. We have one exception for the Baytown Bridge. We have twin beams. We use twin towers connected here. Now we have a complete truss from here to there. That means wind transversely on the cables which run onto the tip and on the cables and on the beam here, these loads create only tension and compression. That's why, in that case, we can keep constant the depths, top and bottom. In this case, we used only 7 feet, 2.1 meters for a 130 meter high tower, a rather slender structure, but it works. Stay cables, very briefly, of course, the main load for stay cables is the tension, and we size it by stresses, service or ultimate. However, if we have the tension cables and then the anchorage rotates because the beam bends due to high live loads, or if we have not installed the cable anchorage in the tangent, we have a sag cable, so we have installed at the stand and at the tangent, not at the secant. There are examples where they've done this mistake. What happens then is the following. If we have a tension member and we rotate the anchorage, then under first order theory, of course, there is a certain bending radius and we have bending moments. But the tension causes this bending radius to minimize. It's pulled together there, and so the stresses, the nonlinear tension, or other way around, the tension has a nonlinear effect of increasing the stresses, which is important for the sizing of the stay cables. Last time when I talked to you about sizing and stay cables, I mentioned these anchorage problems. Practically, we do it like this here. We have the strands fixed, and if we have a rotation, we get some bending moments. So what we try to do is we put in, if that's a stay cable, an elastic support here, or a support, which takes the bending away from the sensitive anchorage. The free lengths can more easily take the kink than the anchorage. So that is a way to reduce these stresses. This was the very basics of calculating the flow of forces in a cable stay bridge. And you should think about it. It is very simple once one gets familiar with it. And we will, in the next lecture, go on and then see what comes from that in complete cable stay bridges. Thank you.